Good afternoon. So I'm here to talk about spell and the spell part of MX sample mounting. First of all, who am I? I'm Gautam. I work on control systems and automation. I'm from Motion Solutions. It's right here in Huntingdale. And as a company, we support motion controllers, drives, motors, linear systems and actuators, robotics, and telematics. We provide custom services for software, electronics, hardware, and mechanical designs. And previously, we collaborated with Australian Synchrotron to create the successful MC8000 for beamlines and cable. So, coming back to the project. So, when we started, we saw that there were several middle-level layers between the graphical user interface and the robot actuation. And fairly complex tasks such as probing and picking, placing samples were compounded by the sheer volume of poorly documented DHS code which we inherited from Stanford. So even simple operations were made extremely complex because of the enormity of the source code. And the enormity just by itself doesn't make it complex. It's because it was poorly documented, it was more complex, and it was hard to debug, and it was almost impossible to find the bug in a reasonable amount of time if any failure occurs. So the maintainer would be doing this. And yeah, so typically how the Epson robot we applied it. So Epson robot, which is used in the MX9s, they are actually a PC-based, like Mark said, it's based on Microsoft, and it's called RC620. And this RC620 Plus natively uses Spell Plus as a programming language. And in a typical application, like packing jobs and everywhere else, all the code is on the Spell layer, and it's all coded in Spell. And the higher level layers are, the interaction with the higher level layers are kept to a minimum. So, as an example, if we want the robot to move from point X and switch on an output and then move to point Y, all these can be written in a function in Spell, and then we could call it from a human machine interface. Just call the function and it does the job for you. But the initial architecture review, where Matthew and Mark was involved in, they found that unlike the typical robot application, the inherited code, it was having a lot of high-level layers, and each specific move was being called from the high-level layers instead of the native layer. And each I/O was activated from higher-level layers. And because it was creating unnecessary overheads in the network, and also because of this, there was more debugging time. And when a robot stops midway through a sequence, it was hard to figure out where the robot was being stuck. So finally, Matthew from Motion Solutions Australia and Mark, they both decided that we need a complete redevelopment of the code, and it should be well documented so that it's easy to use and it's easy to maintain. So in simple terms, this is where we started with. So DHS over there was written in managed C++ Microsoft code, Visual C++ code. And bulk of the robot motions and sequencing functions was present there, and there were about 10,000 lines of spell code which was interfacing with it. So whenever you wanted the sequence of moves to be done, it goes through the DHS server, and then through a VB guide wrapper, it transports those functions to spell, and then spell does the job on the robot. So our plan was to remove this entire picture here and put everything in Spell itself. So all the robot motion commands will be in Spell. And from Epics, you can call, from Python, you call the higher level functions in Spell, and you use Python Epics for message retain. And yeah. So while doing this, what were the challenges which we encountered? So firstly, refactoring and translation. So DHS Visual C++ code. So it had over 20,000 lines of code, and Spell Plus layer had some 10,000 lines of code, like you saw before. And this code was had a lot of branches, nesting, and illegible variable names, and also it was poorly documented. So the solution for that was I used to carry like large A3 size drawing books to make flowcharts and algorithms. So everything is related to a specific task. It fits in one or two pages at most, and so you can see the entire picture in one go and figure out what's happening there. And also experience from Mark, it helped me a lot because he had worked on the robot for quite some time, and he had seen some catches and he shared all those information with me. It saved me a lot of time. And then this one, the small one, Spellbus. Spellbus itself lacks pointers. It's a language, and it also lacks eval functions. The solution was fortunately it had three-dimensional arrays. So our application here required three-dimensional arrays at max, which was for cassette position, or row, and column or port. And because this is all we wanted, so that wasn't much of an issue. But the eval functions issue was handled by Mark in the network server. And the next part was the robot had to be run on high-power mode for certain maneuvers at certain instances, especially like the U-angle maneuver where you turn only the cavity and tail, like that. And running the robot in high-power mode is a dangerous thing while debugging and testing. So there were two crashes while I was developing the robot. And this is one of the crashes. So, solutions for that. Work in a supporting team with supporting team leaders. Tom, Jason, and Mark, they were all supporting. And initially, after the first crash, I was upset, and because I think they have a quote saying, if you don't break stuff, it means that you're not working. So that helps a lot. And that helped me overcome the upset stuff, and I could move on with the project. And the next one was take a lot of videos while you are testing. Daniel and also Robbie, they set up remote cameras and video recording system, so we could go back in time and then see what had happened. And with that, we can track through the code and see where the robot was being behaving radically. And direct Spellbus level coding helps because Spell environment has debugging tools for diagnosis, so we could easily track where the problem is and then just make the necessary change. And finally, the force sensor. This is the most convoluted problem of all. Like what Mark was saying, under the end, this was the one which was giving us lots of issues. The force sensor is being used in different applications inside MX mounting itself. So changes to this force sensor, keeping one application in mind, like calibration, would affect different applications like probing or picking and placing. So the force values received from the force sensor has to be taken at the right time and with the right threshold values. Saying if it has a low threshold value, then we could just detect noise as a touch, and in just free space, it just figures out, tries to think that there's a cassette there, and it's just free space. But if you have a high threshold value, it pushes into the cassette and overpresses it before sensing the touch. And further speed and acceleration of the robot, they also affect the threshold values, and also the difference between the reference point and the place where it's touching the cassette. So you have some errors, and because of this, you'll make some bad judgments on the geometry of the cassettes. So, and finally, once you add liquid nitrogen, everything breaks loose. Right? It's just pain and wobbling. Solution. Have Mark on your side. I think he worked a lot on the force sensor, and he used, like he mentioned before, he used a lot of different statistics, averaging and mean, median, mode, and finally I think he came up with the trend average method. And we also had a routine, that's the same spot routine. What it used to do is the robot used to just touch the pole again and then we used to figure out the stability of the force sensor based on that. And then different strategies were employed to use these force values in the application itself. So, for example, the force was noted before the touch was triggered and after the touch was triggered. And then based on two values, we compared and decide whether it was really a valid touch or not. Benefits of the new architecture. So, like I said before, the spell-based environment provides a lot of diagnostic tools and which helps in investigation and resolution and for DOD. Yeah. And the spell-based code now it can be with the network server, it can be ported to newer Epson robots as well. And so there's no worries on compatibility issues. And it's easy to add new features because the manufacturer Epson, their intention was to use the spell for making the motion commands on the spell on the Epson controller and making the robot move. So they are making changes, and now that it's also documented, and there's also a wiki page on it, so it's easier to see what's going on and make changes at the right spot. Experience. So we started with this project without much hopes, but we didn't think it was possible at first, and then after week 4 meeting, we agreed that it looked possible, and this was mainly because of the convoluted code before and also like limitations in spell. And finally, consistent support from the team, especially Tom, Jason, Robbie, Mark, and Matthew. This translation was possible. And yeah, it was a great pleasure working with you all, and lots of fun. And I look forward to further collaborations with Australian Synchrotron and Motion Solutions Australia to build amazing machines. Thank you.